Hello, welcome to es346 Basic Thermodynamics. These are examples, and the examples today deal with ideal gas entropy. I'm Rorik Peterson. Here's the first example we'll do today. We're told we have a 1.5 cubic meter insulated tank. It contains 2.7 kilograms of carbon dioxide, initially at 100 kilopascals. Work is added until the pressure rises to 150 kilopascals, and we're asked to find what is the change in entropy. So, well, we've got some equations that tell us what the change in entropy is, and we actually have two different ones that we could use. The first one is that delta S is Cp, natural log of T2 over T1, minus R, natural log of P2 over P1. We have another relation that we could use just as well, which says that delta S is Cv, natural log of T2 over T1, plus R, natural log of V2 over V1. And both times here I've written this in intensive form, so this would be per mass. If I want the total change in entropy, I would multiply that by the total mass. I can use either one of these relations, and so sometimes one tool is easier than the other. If I look at this second equation down here, where I have a V2 over V1, this is a constant volume, and the mass doesn't change, so that term right there is 0. So maybe this second equation would be a little bit easier, because I only have one term to include. On the other hand, if I look at the first equation where I have P2 over P1, I'm actually given both of the pressures. So other than having to calculate this in my calculator, it wouldn't actually be that much more difficult. So actually what we'll do in the example is we'll do it both ways and just confirm that both will give us the same answer. Well, whichever tool I use, though, I do see the first term requires the ratio of the temperatures, and I need to determine what that is. And so I'm actually not given any information on that. So let's go ahead and figure out what the ratios of the the ratios of the temperatures are. The mass is fixed inside here, so I can use the combined gas law that says P1 V1 over T1 is P2 V2 over T2. And the volumes are the same, so I can go ahead and cancel those out. And then rearranging this equation tells me that T2 over T1 is equal to P2 over P1. And I know what P2 over P1 is. That right there is equal to 150 kilopascals over 100, or that ratio is 1.5. So there's the ratio that's going to go into both of those equations right there. So let's go ahead and use this first equation right over here and see what that gives us. And so delta S, and I'll go ahead and do this as an extensive form right now, is going to be equal to, I'm going to just multiply the mass by that term that I have. And the first thing I need to find is my heat capacity, Cp. So I need to find the heat capacity of CO2, and I'm not even told what the temperature is. So what we're going to need to do in order to figure out what our value of Cp is for CO2 is we're actually going to determine the temperature. So let's go ahead and find out what T1 is. We're given more information at the initial conditions. So we have P1 V1 over M and R, and so that's going to be equal to 100. I'm running out of a little room here. 1.5 cubic meters, and so the mass is 2.7, and now I need to get a value of R for CO2. So let's go to our tables, and okay, so what we need to do is go ahead and scroll down to find out the value of R for CO2. And so my value of R for CO2, I see it right there at 0.1889. So this value here is going to be 0.1889. Sorry, that's getting kind of crammed over there. And this number right there is equal to 294. This is an absolute, so that's Kelvin. So that's the initial temperature. Final temperature is 1.5 times that. So we know that T2 is going to be on the order of 450 Kelvin, which means that my T average, which we'll go ahead and use to determine our heat capacity, is going to be in the order of, about 375 Kelvin. All right, so let's find out what the heat capacity is at 375 Kelvin. So now we need to go down to table A2. And here's my carbon dioxide, and 375 is going to be somewhere in between 350 and 400. So my Cp value somewhere between 0.895 and 939. So if I go ahead and average those values, I did that, and Cp is about equal to 0.917. And since we're going to use the second equation, I need to know what Cv is as well. And so I'm going to go ahead and find my average value of Cv. So now I'm going to be averaging 0.706 and 0.75, just find the average value in between that. And that's about 0.728. Okay, so now I can go ahead and put that CP value in there of 0.917. This is the natural log of, well, that ratio is 1.5. And then minus my value of R, I looked that up at 0.1889. And then I've got natural log of the ratios of the pressures, which is also 1.5. So there's the first one. And this value of the mass, that's 2.7. So that's 2.7 kilograms, goes right in there. If I do that arithmetic, this is 0.797. And the units on that are going to be kilojoules per Kelvin. Okay, so let's go ahead and verify that if I use this second equation, I should end up with the exact same thing. So delta S, and this again will be my extensive, and I'll multiply that by the mass, my 2.7 kilograms. All right, and now I don't have this second term, so all I've got is my CV term, 0.728, and the natural log of 1.5. So just a little bit less to type into my calculator. If I do that, I find out I end up with the exact same answer, 0.797 units of kilojoules per Kelvin. So what I saw is I can go ahead and use either one of these equations, and that's true every time. These are just two different tools that do the same thing. I think of it like a metric wrench and an English wrench. They both turn bolts, just some work a little bit better in different situations. Okay, so let's go ahead and do a second example here. And in this example, I've got, again, an insulated tank, and it contains 4 kilograms of argon gas, initially at 450 kilopascals and 30 degrees Celsius. Argon now escapes through a valve, looks like there's a valve here on the top, until the pressure inside is 200 kilopascals. And assuming the argon that's remaining inside the tank underwent a reversible expansion process, so it's reversible and it's insulated, which is adiabatic, we want to find the final mass in the tank. And so these are some important words. It's reversible and it's insulated. Insulated meaning adiabatic, just another term for that. So what I know from that is that those two mean my change in entropy is going to be equal to 0. And so we just had those same two tools we used last time. One of them was CP, natural log of T2 over T1, minus R, natural log of P2 over P1. And the other tool I could use, and that entropy is clearly also equal to 0, is CV, natural log of V, that's T. Go ahead and erase that. Natural log of T2 over T1 plus R, natural log of V2 over V1. All right. So I could go ahead and use either of these, and what I'm trying to find is the final mass. I'm trying to find my final conditions in here, and I know that my final pressure is 200 kilopascals, so there's one of the final conditions, but I don't have any information about the final temperature. So what we want to do is we want to think about kind of what's going on here. So if you think of, there's going to be maybe some little small mass of material that was right here in the corner, and then as this expanded, it ends up filling the whole thing in here, right? Okay, so there's the new final material there. Some small mass to a larger mass. And so its specific volume, this term right over here, is not 0. So in this problem, this term right here is not 0. So I can't go ahead and just cancel that out. So either I'm going to use this second equation where I need to find the ratio of the volumes and temperatures, or the first one. And the first one here is going to be easier because now I know the pressures. It started at 450 and 200, so I know two of those values, and all I need to find is T2 over T1. So turns out this first equation in this problem is going to be easier to use. So I'll go ahead and use that. And we could rearrange this equation. We saw that in one of the videos. This equation right over here ends up with a little simpler form, which is this. T2 over T1 is equal to P2 over P1. And this is to the K minus 1 over K. And remember that K is just the ratio of the heat capacity, Cp over Cv. And I know what P2 over P1 is. So that's P2 is 200. P1 is 450. And so I need to find the value of K for argon. So let's go to our tables to do that. And looks like I've got to go up here to A1. And oh, there's argon, A2A. There's argon. I'm looking for the ratio of the heat capacities, 1.667. Okay, so come back over there. This K is 1.667. So K minus 1 is 0.667 over 1.667. And if I go ahead and do that, that ratio of those temperatures is 0.723. So that's what T2 over T1 is. So I can now go ahead and find out what my final temperature is. T2 is equal to this 0.723. And my initial temperature was 30 degrees, so I multiply that by 30. Remember, I've got to convert this to absolute, so that's going to be add 273 to that, and that comes out to be 219 Kelvin. So the temperature goes down, and that's a kind of a gut check here, because this thing is expanding, it's insulated, it's clearly losing energy, and so the temperature going down makes sense. Okay, so let's remember where we're going. What we're trying to get. We're trying to find the final mass. We're trying to find M2, and we're going to get that from the ideal gas law, which is P2 V2 over R T2. We just found T2. P2 was given in the problem. We need to know what that final volume is, which is, what's the volume of this entire tank here. And that's actually not given in the problem. In fact, we're going to have to figure that out, or we're going to figure that out with my initial conditions, because the volume is constant. So the extensive volume V2 is equal to the extensive volume V1. And so what we're going to need to do is determine what V1 is first. So V1 is equal to MR T1 over P1. So put our numbers in there where we were initially. This has 4 kilograms, and my value of R is 0.2081. All right, that's for CO2. And my initial temperature was this 273 plus 30, or 303. And then I'm going to go ahead and divide that by my initial pressure, 450 kilopascals, giving my initial volume 0.5605, and that is cubic meters. And those are the same, so now I can come back up to find M2. So now my pressure went down to 200. My volume stayed the same at 0.5605, and dividing that again by R of 0.2081, and then my final temperature 219. I found 219. I already found that. All right, so that's going to give me what my final mass is, and my final mass is 2.46 kilograms. So I started off with 4, went down to 2.46, so about 1.54 kilograms left the system. And that completes this problem.